Is now being recorded.
As well prepared. I'm going to talk a little bit completely ad hoc about data in complex terrain. Basically, when you think about snow in the mountains, in my experience, the hardest thing to get is to figure out how much snow is falling from space and then how fast is that snow melting. And so I'm going to talk for a few minutes here about some of my work on figuring out where do you get data if you want to figure out snow in complex terrain. And what you see here on the screen are just some examples of, there's a temperature sensor in a tree, because those of you who know me know that I like to put temperature sensors in trees. It's a picture of one of the Met stations in California after a particularly wet winter, not this winter, and a picture of a snowpack lower right-hand corner snowpack evolving over the year, and a picture of spatial patterns of precipitation in complex terrain. So an overview of what I'm going to talk about is first, when you go to the mountains, how do you get distributed driving data? And by driving data, I mean the things you would need to run a snow model. How do you figure out how much snow is falling, how fast that is melting, and should you use a dynamic model, something like the weather models you might watch on TV, the weather research forecasting model, versus empirical techniques where you might take a station and then extrapolate that data over terrain. What I want to talk about in terms of, you can see that you can think of a snowpack, and this is, if you listened to Matthew Sturm's talk last week, we're talking about much deeper snowpacks with much different dynamics than in the Arctic. Here you can see snow accumulation season occurs during this time of year, except as I'm showing a picture from California, not as much as we might hope right now. We have a season where the internal energy balance of the snow is changing and the snow temperature is changing, and then we have a period at the end where the snow is melting and the snow disappears. And this typically happens every year. I'm going to show you a little bit about how do you account for these different seasons, and using examples from my personal two favorite basins in California. And I'm guessing Jeff is probably showing some of the same basins unless he's completely focusing on the Himalayas, and the American and the Tuolumne. So the first thing you need to think about is the accumulation season. What really is controlling how much snow is accumulating in the mountains? And I've found over time that it works much better to take a dynamic approach. First, you really need to understand the upstream boundary conditions. What you see here in A is a picture of an atmospheric river impinging on the California west coast. This is a map of integrated water vapor, and basically these are narrow streams of very intense moisture that come and pound on the west coast. Once that stream of moisture lands, you see in B, we need to really think about the dynamics of the system. I've drawn here in yellow a number of different air parcel trajectories. You can have an air parcel, travel up over the mountain, or an air parcel, as shown in number 2, may go and hit the mountain and be blocked, in which case it will turn and form a barrier jet going traverse along the mountain. Or, in the case of the Sierras, you may have moisture that travels around the mountains. Here I've drawn a picture wrapping around the south side of the Sierra Nevada. And these are some of the storms that actually flood Utah and Salt Lake City. After you know where that moisture is going towards the mountains, you really need to think about the microphysics. Matthew Sturm last week talked a fair bit about snowflakes, and this is just a picture of some different snowflakes. If there are very light, fluffy snowflakes, they're going to fall out of the sky more slowly than hail or graupel. That's going to determine how far that snow is transported up the mountain range. Does it make it to the lee side? Does it get over the mountains, or does it fall on the windward side? In some place like California and other warmer climates, you really need to also consider the phase of the precipitation. Where is it falling as rain? Where is it falling as snow? And finally, as you get very close to the surface, you need to consider complex terrain and dynamical wind effects of where that snow is deposited. And here you can see that more is scoured where it's windy on the windward side. Some's deposited under the trees, and some's deposited just in the lee of a sort of bump in the mountains. So I'm going to show you some results here from the Weather Research and Forecasting WRF model, which was run by Mimi Hughes at 6-kilometer resolution over California with reanalysis boundary forcing. Basically, that assumes we know the weather coming in, and we're going to assume we had a perfect large-scale forecast. How would we downscale it to the mountains? This model, obviously at 6 kilometers, does not include any of the very fine-scale surface deposition processes. For comparison, if we're running a hydrology model, we might also take a more empirical approach where, in average, we would assume that precipitation increases over a basin. Here I've shown on the left plot there's an average increase, which can be fit to station data, where it might be very low at the bottom and increases as you go up the mountains. And then temperature, the sort of average temperature lapse rate over the globe is a decrease of 6.5 degrees Celsius per kilometer. And so you would use an estimate of precipitation and temperature to figure out all of these different dynamics and how they might interact on the mountain range. And the comment that says see Mark Rowley's talk, I don't think he's planning to actually talk at 6:30 this afternoon. So one way we do with commonly distributing precipitation in mountains is to use something called PRISM, which probably many of you are familiar with, developed by Chris Daly at Oregon State University, where he basically is assuming that elevation influences both temperature and precipitation distributions with climate. He uses terrain-induced climate transitions, assuming you have topographic facets and a moisture index. What does that mean? That means that your west slope of the mountains is going to be wetter than the east slope of your mountains. And when you're interpolating, you want to interpolate, on the same slope. He assumes persistence of climatic patterns, which is climatologically aided interpolation, which basically means that he uses a climate map instead of a digital elevation model as a basis for the other maps. This means that PRISM in general, it's trained on observations, and so it does very well in years that are like the norm, and it misses years that are quite different from the norm. Just to emphasize that, the next bullet says it assumes spatial patterns are repeatable in time. So this is some work done by Nick Wayand in 2013, showing that just basically was a big bake-off. I've been told that it's too girly to call things a bake-off, and I should call them death matches. So maybe it was a death match between WRF and PRISM. And basically went somewhere in Northern California. We had a lot of observations, and we tried to figure out, what's better. Should we use a dynamical model, or should we use the more statistical techniques? The answer is, in terms of temperature, annually they both did great. The upper plots here show they all match. However, in terms of precipitation, we were fundamentally confused. Annually, the performance really varied. So here you see, on the left, you see a year where PRISM matched the observations much better. And, we also don't have very many observations in the mountains is always a problem. And in 2006, it actually looked like WRF did a lot better. However, 4 observations are hard to know what's going on. And if you look at the stream flow, that these observations in terms of what we've got here is cumulative stream flow, the total amount of water that flowed off of the mountain over a year, and what would be predicted if you were to run a hydrologic model using WRF as forcing versus using PRISM as forcing versus the observed total stream flow. And it's interesting that even though PRISM looked much closer to observations in 2003, the stream flow observations actually over the total of the year came closer to matching WRF. One thing we know is that you put a precip gauge in the mountains and they're very subject to undercatch. There's also one gauge that's showing quite a bit more at higher elevations. So stream flow may be our best estimate of what actually happened. When you think about using these things, as I mentioned, PRISM goes back to climatology. Therefore, if you look at long-term climatology, PRISM is great. We actually are getting the amount of precipitation, which in this case is snowfall, in the northern Sierra Nevada. And you can see here's a map of PRISM here on the left. On the right are just colored dots of all the observations. It matches quite well. And how precipitation increases with elevation matches quite well. However, when you start looking at individual years, you can see that some years are not a good match. For example, I'd like to highlight 2007, where you look at PRISM, and there's also a plot from a linear model, which I apologize I won't go into, as well as observations. And remember, I mentioned that observations are very prone to undercatch. So here we have overcatch at a lot of basins. And so, well, it's not overcatch. I apologize. I'm a little bit off my game doing this last minute, and if you hang up, I forgive you. But here what you see is that the observations, which are prone to undercatch, so usually the actual amount of rain that fell would be more than what these measured if there is an error, are showing about twice as much or more precipitation at higher elevations than would be predicted in 2007. So it turns out that actually what is being missed when you do this is changes in the dynamics of the situation. So I remember I showed you that what can happen as these weather systems come and impinge on the Sierra Nevada is that you can get a mountain parallel barrier jet, and it turns out that that barrier jet influences, what you see here is the yellow line going up over the top of that, it influences the distribution of precipitation over the mountains, such that if you average together all days of precipitation, they match the mean values from PRISM. But if you look just at days that have a low altitude barrier jet, that basically means that there is a very shallow layer of air traveling along the base of the mountain range, and it's forcing the air to lift and rise earlier. It's causing more turbulence and more mixing and updrafts. And in that case, what you're getting is a much enhanced increase in precipitation at higher elevations. This is something that a mesoscale model can get that statistics cannot. So in terms of hydrology, right, we want to see a hydrograph. Does this matter? So it turns out that that here is a very simple model of the Yuba Basin in Northern California. And you see in January there's a really big rainstorm. It's a rain on snow flood. And then you can see the rest is melt runoff in the hydrograph. And what I've done here is I've run a simulation with climatology, assuming that precipitation is always distributed the same, with a low Sierra barrier jet, which is putting more precipitation at higher elevations. This was what was observed, what happened in 2007, and with over a year where the precipitation distribution varies according to the observed altitude of the Sierra barrier jet. No, I didn't go into, there's also a high elevation Sierra Barrier jet which blocks the higher altitude precipitation and ends up with less precipitation at higher elevations. So what you can notice is that this actually has the greatest impact during a wet, warm storm. So here you can see that in this case we had a major rain on snow flood in the area, and that if you look at climatology in the blue, that the barrier that actually occurred caused much more runoff. That basically precipitation all the way to the summits contributing to stream flow, and we have greater orographic enhancements. We have more rain than would be expected. There's a common thing. I grew up in California, and people, there's kind of this debate always going of how much snow melts in a rain on snow flood, and some of the forecasters have said, well, it doesn't look like that much snow at higher elevations is melting, but there's more water coming out there than we expected. Where could that water actually be coming from? And if you look at this, it turns out that if it's actually raining harder up there, due to the dynamics of the storm, that would explain more water even without snow melt. So as we go further south in the Sierra, we get more complex topography and more involved dynamics of how much snowfall we're getting, how much rain we're getting, where we're getting rain versus snow. If you just sort of think about a storm as moisture impacting a mountain range, the northern Sierra is this very nicely behaved slab relative to the predominant wind direction, whereas the southern Sierra, basically has almost, two bumps to the range. There's sort of what I call the front and the back side in Sierra. And so you'll get some areas that, drain to the west that are in the rain shadow, whereas the air goes over it, it's sinking, and you're not getting uplift and condensation. So this can create some very interesting patterns. So here we're traveling to the southern Sierra, way down here at the highest altitude. That's where Mount Whitney is. What I've highlighted here in the black are, this is Yosemite National Park, and these are two basins, the Tuolumne Basin and the Merced Basin. And what you see here are, in many years you get patterns where what I've highlighted here on the front Sierra are all, and what you see here, first let me slow down. So we have all of the circles are snow courses. All of the black dots are precipitation gauges. First thing to note is those black dots don't go very high up in the mountains, and as you go further south, you get a lot less of them. However, we have a lot of snow courses up in this area, and there are a lot of years where you get patterns that shift. I hear people talking. So they shift, so some years the front has significantly more snow accumulate, and in some years the back has more accumulate. So here's an example of 2 years. So here are, two snow pillows in my favorite location. These are what you see on the right. This is how snow water equivalent in millimeters over the year, and you can see, snow accumulates and melts. But the amount, we've talked about PRISM assuming climatology relative to other places. The amount is such that in 2005, there's significantly more snow at Gin Flat, and 2006, there's significantly more snow at Tuolumne. Basically, in this area, the pattern shifted between those 2 years. So part of that, whenever you think about snow accumulation, as I talked about, you have to think about rain versus snow. Right? And 2005 was a colder year than 2006. Particularly, notice that all the storms in California occur right on New Year's. The forecasters tell me that it's just because they will never actually get a nice holiday around that time of year. The New Year's storm in particular in 2005 was a much colder storm because the front Sierra is a lower elevation. However, it's not just a pattern of that there was more snow because it was colder at those lower elevations. It also, there was a total amount of water in the area near Gin Flat than in the area in the Tuolumne. And if you look at, I've drawn two river basins here, and you can think about river basins as being sort of giant precip gauges or that integrate all of the rain and all of the snow over the year. And you can see that the Merced River, which is this one right here, and the Tuolumne River, which is the one to the north, usually if you normalize the basin area of about the same amount of precipitation, about the same amount of runoff. You can see in 2005, they look like they're the same basin. They just plot right on top of each other. For in 2006, you're getting about 15% more runoff, particularly through rise in Tuolumne Hetchichi in 2006. That was the same year that you saw significantly more snow in the back gauge. So what we're doing is we're trying to analyze how this is happening dynamically, and it turns out that these were very different storms. The 2005 storm arrived from the south. It flooded LA, and then it hit basically with this very southwesterly storm track direction was how it came in, whereas the 2006 storm actually came in from the north. It flooded the northern Sierra, the Yuba and Sacramento area, and then it hit much more on the northern end of Yosemite. And so the statistical techniques break down, and we have to understand storm dynamics. This is showing how the weather research forecasting model is representing the total annual precipitation between those 2 years. Again, 2005 was the one that had the big atmospheric river storm coming from the south. So you can see, particularly as you go down to the very southern extent, there's a lot more precipitation, whereas 2006 had the big storm coming in from the north with much more precipitation up here. And our basins of interest, I'm showing you, again, the outlines of the Tuolumne and the Merced with marks for Gin Flat and Tuolumne Meadows, sort of sat sort of right in the middle of that change of where storm tracks. Why is this so important is because these two storms, if you go back and look at these snow pillows, when are they rising? That the entire snowpack in the Sierra is really explained by 1, 2, 3 big storms of the year, and particularly really over 50% of the precip in both years was explained by one storm. That one storm is quite different. You don't average out the spatial patterns for your snowpack. So this is just highlighting again that WRF is starting to get the general pattern, but isn't exactly matching by a point gauge. And so we're thinking that rivers are a better way to sort of interpolate and understand than just a point. A path forward for better understanding snow accumulation in the mountains. When our standard precipitation gauges start dying, one of my students in his defense said that conditions that are good for snow are bad for rain gauges. And when we really want is stream flow, and this is a picture of Tuolumne Meadows in Yosemite next to that, the Tuolumne gauges right back there by Lambert Dome. The in the mean averaged over many years, both dynamical and statistical methods of understanding the rain and snowfall in the mountains works well. However, at basin scales, much smaller, annual precipitation patterns often deviate from the mean, and the statistics break down. WRF generally gets the dynamics right. It is putting more precipitation at higher elevations during low-altitude barrier jets, and it is shifting the precipitation similar to observations in the southern Sierra. But often its precise locations and timing are off. So we need techniques to improve WRF at the basin scale as well. And part of the needs for that improvement, finding enough validation data to even know which in an ensemble of runs is correct. Really, we need to work closely because our statistics will never be able to account for things that deviate from the mean unless we can put out enough gauges to sample everything. So we really need to work with atmospheric scientists to improve the model for both snow and hydrologic applications. how am I doing time-wise? Because I think I still have a little bit longer. The other thing, if we get snow accumulation, which is a terrible problem, the next thing we need to think about is the energy balance. What is going to melt our snow? And if you watched last week and saw the Alaska snowpack, that basically the snowpack was very thin, and the accumulation season was most of the story. Once it got warm enough to melt that snow, it's thin enough and it warmed fast enough that it's gone in a few days. However, in most of our mountains of the western United States, we accumulate a large enough snowpack that, you know, I am based out of Seattle and go and this year again is an anomaly that go and dig a snow pit that's, you know, twice as deep as I am tall. I tried once to do a snow course at Paradise on Mount Rainier, and after digging and digging and digging, I gave up. I think it was over, like, it's definitely, I think it was about 6 meters deep of snow. But if you have that much snow, then the melt timing starts really mattering. How fast will that melt be gone, and how is that going to evolve over the season? It's going to take a long time to melt that snow, and that is our water resources for all of our cities, for our hydropower. We want to know the dynamics of what's happening. So what I'm showing is ways we've been working on how do you get the energy balance right. So when you think about what melts snow, you need the snow to warm up to zero. It has to be isothermal and ready to melt. So what you're looking at here is a graph of a model simulation of the snowpack over the year, and orange is warmer and blue is colder. And this is a pretty warm region snowpack, but you know, before melt to occur, you need the snowpack to go orange is isothermal, ready for melt. And so during the snow melt season, it's isothermal. This is not interesting. But during this intermediate season, you can actually see that there's a lot of texture and dynamics going on, and you know how the snow is getting colder and warmer with different days. And basically, you can start using the snow surface temperature as an integrated measure of the energy balance going into and coming out of that snowpack, and get an idea of whether you're putting the right input into melting the snow. So here's a picture of how we might model the snowpack energy balance. And so here's basically the components are long wave radiation in, long wave radiation out, short wave radiation in, which is reflected by the high albedo of snow, and sensible and latent heat pack. All of these at the surface control the snow surface temperature right here, which I've shown as TSS. And you can see that during a time, this is a simulation where we're varying the incoming long wave radiation, which is basically one of the hardest components to physically measure in the mountains. I've found more broken long wave radiometers than almost anything else, except maybe precipitation is harder. But that's hard to measure, but the snow surface temperature is actually pretty robust to measure. And what you see over here is there are two simulations of a model with two different long wave inputs, and you can see that during this period in January when the snow isn't telling you anything, the surface temperature of the snow is differing by 15 degrees Celsius. So you can start getting a measure of if you are putting the right forcing to melt your model in correctly before the melt season starts. I found most long wave sources are in general biased, and so if there's a consistent bias, you can correct that early in the season. Mark Rowley, I apologize, this says submitted. It actually is in press now. It's Rowley et al. 2013. And he showed that if you ran a model, he used SnowTherm, which was developed by Rachel Jordan, and you imposed, you ran the model with, he ran it at Col de Port in France, where they have a very nice data set. And if you ran it with all of the data, that the modeled snow surface temperature matched the observed extremely well. However, if you gave it biases in long-wave radiation, which is easy to do if you're in the remote mountains, that your snow surface temperature with a minus 10% bias showed the model was biased low, and in cases where it biased with high radiation, it was biased high. And so you could actually use a bias diagnostics of modeled versus observed snow surface temperature to figure out your energy balance forcing for your model. And this is a picture of Mark. So the path forward for MELT is to start looking at measuring snow surface temperature and compare it to your modeled snow surface temperature. We found it's also very useful to predict surface hoar formation. This is a picture of me climbing our energy balance station near Snoqualmie Pass in Washington, and that's a spot where we're working with the avalanche team, and they very commonly get surface hoar form and then be buried, which is an avalanche problem, and the IR sensor can pick that up very well. And then I will end this here and open it to questions if anyone is still with me. And this is just my thought about the mountain energy cycle from precipitation to rain versus snow to snow distribution to melt rates and energy balance to snow disappearance and stream flow and stage. And thank you. Is anyone still there? I can't even see the regular.
Hi, Jessica, can you hear me?
I can hear you, yes.
All right. So if anybody has any questions or anything, if you could type them in, we can iterate on this like last week.
No questions?
Okay, one just popped in. All right, so when modeling snowpack decay, what do you find works well to account for sublimation?
Oh, what works well for sublimation? That's an excellent question. I think the jury is still out about what works well for sublimation. In my experience, I showed you a little bit about techniques to get our radiation better. In terms of getting our turbulence better, we still have a long way to go. The parameterizations deviate quite a bit. Places I work in the Sierra Nevada and the Cascades, the air is moist enough that we don't get a lot of sublimation. Right now I'm on sabbatical in Boulder, Colorado, and I basically watch it snow outside my window, and it's all gone the next day, and there are no puddles. So clearly it all sublimated. I think that's definitely an open area for more research, and I'm not sure how to do it yet.
Okay, we've got another question. Did the difference between the 2005 and 2006 storm track generate different temperature patterns in the southern Sierra between the 2 years?
Yes, it did. Let me go back here. The interesting thing is that intuitively it actually is not what you might think. 2005 had this storm that came from the south. 2005, if you go look in the news, that flooded Los Angeles. And intuitively I would think, oh, it was a storm that flooded Los Angeles, it must come from the south, it must be warm. Actually, that was a very cold storm. It actually was a wraparound low. It had a lot of Arctic air mixed with the tropical air, and it actually was snowing during that big event at all of these sort of front range, lower elevation snow pillows. Whereas in 2006, the storm that hit the northern Sierra, it actually had more of a tropical component, and so it actually was a warmer storm. It still snowed. I mean, the southern Sierra is so high that it still snowed there, but in the northern Sierra, it was raining all the way to the it was raining all the way to the crest in the northern Sierra. This 2006 storm was also the one that I actually showed right here. This is 2006. You can see it had the low altitude barrier jet, and it also had enhanced rainfall at higher elevations in the northern Sierra.
Okay, and now we've got a question from Lee. What are current approaches for modeling rain on top of snow events? Any special consideration for such events?
Yeah, so someone asked about sublimation. The opposite of sublimation, condensation on the snowpack, is actually one of the main drivers triggering snowmelt during a rain on snow event. Danny Marks has a really nice paper. I forget the year, but it was about the 1996 rain on snow event in Oregon, and showed very nicely that really wind and turbulence, and particularly the combination of sensible heat flux, which is warm wind, and latent heat flux, which is actually the condensation of droplets on the snowpack, were the primary causes of melt. So something that does not, I mean, we're not very good at getting wind right in the mountains. And again, I mentioned before, we're not so great at turbulence, and that's, some of our larger uncertainties. Things that, aside from turbulence, that are more easy to tackle are getting the rain-snow line right. It actually changes very drastically when a storm impinges the coast. You have to think about it. I hydrologically often think about things as sort of mean storm conditions, when in reality, each of these storms has different sectors. There's a warm sector and a cold sector, a warm front and a cold front. And so over the course of hours, you can actually see the elevation where snow is transitioning to rain varying by as much as 1,000 meters over the side of the mountain range. And somewhere like the Sierra, that can drastically change your contributing area in the storm. So that's actually one of your first modes of concern, is figuring out exactly how much area of your basin is contributing to rain, because that's going to be your flood.
Okay, Jessica, we have another question from Jonathan. What do you think is the source of the negative bias in downward long wave in the wharf output?
The wharf output. So the very sad thing, the very sad thing about this plot is that at this site and time, I had no observations of surface temperature. So what you actually are seeing here is empirically estimated long wave, where the basic thing you do is you look at temperature and humidity, make some guess whether you have clouds or not, and realizing that water vapor is our primary greenhouse gas, make some estimate of long wave radiation. WRF is doing the same thing, where it is looking at the vapor fields in it. So what you're seeing here is I don't actually know which of these two is correct in this instance. If I had bought that $700 sensor and put it out, which I'm now doing, I could tell you whether WRF was biased low or not. I don't know. WRF might actually be right here. But it is what's happening is that actually during this period, this is in the northern California, and as I said, I grew up in Sacramento, and this is January. And January in Sacramento, we get something we call Thule fog, and it is like the thickest, densest fog that settles over the Central Valley of California. And if you're getting depressed because it's foggy there and you're California who needs sunshine, all you do is you drive up the you drive up in the mountains, and you eventually get above it, and it's sunny. And so I think what's actually happening in this case is that there's fog over part of the basin, which drastically increases your downwelling long wave, and there's not fog up places. And I think the placement of where those clouds are is actually wrong in one of these methods, but I'm not sure which.
Okay, and while we're on the long wave topic, there's a question from Bruce McGurk. How does albedo and dusty snow affect long wave measurement? That's
a really good question. Well, I mean, I think that the long wave is trying to measure the surface temperature. The thing you have to realize with long wave is that your instrument is measuring a brightness temperature. And a brightness temperature, if you remember your physics class, is epsilon sigma t to the fourth. So epsilon is the emissivity of what you're looking at. Now, water and snow and ice all have an emissivity close to 1, which makes our life pretty easy. Minerals, however, have vastly different emissivities. I'm not organized at the minute, but I have some pictures of rocks, and you can actually, with an IR camera, and you can see that different grains on the rocks are drastically different colors, and that's reflecting different temperatures, and you touch the rock face and it all feels the same temperature. Really what's happening is that because the emissivity can be so different, you actually will record very different brightness temperatures, and you have to correct for that emissivity. You have to know what you're looking at. Dust is, I'm guessing, some kind of mineral content, and you would have to know the type of dust and its emissivity and how much it was on the snow. So I would think in terms of your sensor actually giving you the true temperature of the snowpack, I would be a little bit nervous. But it's something we could probably figure out with a spectrometer, which Tom Painter, I'm sure, has next to all his dust.
Okay, and now we've got a question from Mike Durand. How much of the uncertainty in WRF precipitation is due to the reanalysis boundary conditions, and how much is due to the precipitation physics, parameterizations, or other issues?
So Mike just hit my my latest proposal right on the head. We are just starting a project in 1 month to study that. Mimi is going to run an entire suite of WRF simulations over the domain, varying boundary conditions and varying microphysics, and we're going to see what we get. So ask me in a year or two, and hopefully I have a really good answer.
All right. It looks like we don't have any other questions.
Excellent. Then I will, since I was